So the formula that we just saw, as it appears in the book. Now in the book, by the way, it's kind of as a footnote at the bottom of the page. The book actually stresses tables like it does for compound interest. They work the same way as what we've been doing here. But the formula as it appears in the book would look like this. Future value is equal to that payment amount times, I don't remember the page. It's at the bottom of the page in a footnote. I'll look it up here in just a second for you. 1 plus R. The R they use is assumed to be the annual rate divided by the number of payments in a year, or number of periods in a year, to the power of N or T or whatever they put. That is assumed to be the number of periods, the year times the number of periods in a year, minus 1 over R. Again, that's the rate divided by the number of periods in a year. So what they put in the book looks very different from what I showed you. And I'm well aware of that. It's just, how do you enter this into a calculator? No, and we're not going to be doing it out, by hand, doing order of operations step by step, because the round off errors would kill us if you're doing step by step and punching it back in every step. So we're going to be doing it as one continuous formula like I've showed you. What page in the book? Good question. Let's find that here. So this is chapter 14. The table for the annuities is on page 501. If you look below the table, there's that little formula. That formula is actually just how they get the compound annuity factor. I'm trying to see if there's a better formula here somewhere. No, it doesn't look like they have the formula better anywhere. So that is the only place that formula appears, is at the bottom of that little table. But anyway, kind of like with the compound interest, or the book stresses the tables, I'm going to be stressing the formulas. Because they do have the formula on page 508. They have the formulas there as well, and some examples with them. But again, they're pretty basic examples. So the way I have the formula written out, I know it appears very different than the book, but it's a lot more usable definition. So let's do another example quick. Let's say that Tim pays $100 a month into a 9.3%, we'll even say the word here, ordinary annuity, for 20 years. Find the future value.
I think you put 200 years.
No extra charge for the extra zero. No extra charge for the extra zero. We'll throw that one in for free. Yeah, that would be a pretty impressive balance, though. Start investing now for your great-great-great-grandchildren. That future value is going to equal your payment amount. How much is that? $100 right there, the payment amount. Times, remember, 3 parentheses, 3 open parentheses. 1 plus what? 0.093 is our rate. Divided by? Careful. The payments are made each month. So divide by 12. Remember, the compounding period is assumed to be the same as the payment period. So if the payments are made monthly, interest compounds monthly. To the power of
12.
12 per year times 20 years. There you go. So 240. Then minus 1. Close parentheses. Divided by. Open parentheses. What goes in here?
0.093 divided by 12.
0.093 divided by 12. Close and close again to finish off our parentheses. So 100 times 123. 1 plus 0.093 divided by 12. Close. Power of 240. Now again, many of you have to use this right arrow here. Once you're in the exponent, to get out, you use the right arrow. Gets you out of the exponent. Minus 1. Close parentheses. Divided by. Open parentheses. 0.093 divided by 12. Close and close. 69, 391, 49. So $100 a month for 20 years will get you close to $70,000. Bless you.
Why do you only need to put 2 parentheses rather than 3?
Good question. If you look at this, I've got 1, 2, 3, 4 open parentheses, right?
Yeah.
I have, throughout the course of this, 1, 2, 3, 4 close parentheses.
This is.
Yeah.
Okay.
You bet. So, Kelly pays $100 a month. You don't know if it's a man or a woman, do you? Into a 9.3% annuity due for 20 years. Find the future value. Well, some of you might be thinking, that's the exact same problem we just did. What's different? Yes, the first one was an ordinary annuity. It's Kelly instead of Tim. That's definitely different. The first one was an ordinary annuity. This is an annuity due. An annuity due means that those payments are made at the beginning of the period. So the difference, very, very, very subtle, very, very, very small. The future value for an annuity due is equal to the payment amount times 1, 2, 3. This first part's going to look very, very familiar. 1 plus R divided by N. Power of NT minus 1. Or NT, and then minus 1, close parentheses. So far, that shouldn't be any big surprise. I'll give you a second, because I know I was getting motor mouth there. Still divided by... I shouldn't be putting numbers in here. R divided by N, close and close. Hey, so far that looks really familiar. That's actually the whole formula for the ordinary annuity. The annuity due tacks onto the end times 1 plus R divided by N. That's it. So for Kelly, this is going to be 100 times 1, 2, 3, 1 plus 0.093 divided by 12, close parentheses, to the power of, still 240, minus 1, close parentheses, divided by, open parentheses, 0.093 divided by 12, close and close, times 1 plus 0.093 divided by 12, close parentheses. Comes out to 69, 929, 27. Now I took a shortcut there, so I'm going to wait a second for you guys to punch that in to verify. Everybody get that same number?
I'm still doing this.
Okay, we'll give you a minute. There must be some.
Yes, I did.
Okay.
Yes.
There must be some weather issues somewhere because we're having some spotty problems on the network. Some sites are blacking out. New Richmond, can you still hear me even though I can't see you?
Yep. Yeah.
Okay.
I wonder if you might be delayed because you said bless you about 5 seconds after I sneezed.
Okay.
Oh, yeah.
10 seconds late.
That's possible. Okay.
I thought maybe you were just kind of losing it.
Well, that's possible too. You'll see here the difference between an ordinary annuity. The amount of payments that's made in is exactly the same. They pay $100 a month for 20 years. That's still $24,000 that's paid in. But the ordinary annuity gets, well, not quite $600, $538 or so more. And the reason is because that ordinary annuity, the payments are made at the beginning of the month. So at the end, there's one extra month's worth of interest. All this little thing that gets put on the end here that's just figuring 1 month's worth of interest. Is all that is. Compounding the interest for 1 more month, 1 more period.
You want to be divided by 12.
Because it's only a 12th of a year, it's 1 month instead of a full year.
Okay.
Kim wants to have $300,000 to retire in 25 years. Bless you. At 8.3%, how much does Kim need to invest each month to reach that goal? Now, before, up above here, we knew the payment and we were finding the future value. The formula was to take the payment and figure out the future value. Here, we know the future value and we want to find the amount of the payment. The difference is exactly the same as the difference for future and present value in compound interest. So to find the amount of the payment, it is equal to the future value amount. What do you think is going to come now? Instead of times, divided by. The rest of the formula is exactly the same. 3 open parentheses, 1 plus R divided by N to the power of N times T minus 1, close parentheses, divided by parentheses, R divided by N, close and close. So let's look at this particular example for Kim. Kim wants $300,000 divided by 1, 2, 3. 1 plus 0.083 divided by 12. Close parentheses, the power of 12 times 25, right? 12 periods a year times 25 years is 300. Minus 1, close parentheses, divided by, open parentheses, 0.083 divided by 12. Close and close. So 300,000 divided by 1, 2, 3. 0.083 divided by 12. Close, power 300. Arrow out, minus 1. Close divided by open. 0.083 divided by 12. Close and close. $300.38. Because it's not an annuity due, it's just an ordinary annuity.
Okay.
That's a very good question.
Very good. All right.
So what do you think?
Good. What if this was a question on a game show?
That would be one really nasty game show.
Yeah, wouldn't it?
Those odds would win a lot of money.
They'd have to make the Jeopardy theme song longer to give people time to come up with the
Yeah.
answer.
No, make it one of those crazy Japanese shows where if you get the wrong answer, you get thrown in a tank full of angry bees or something.
Oh,
I was
yeah.
just thinking that.
You're giving me ideas for my classroom for next year. You do realize a math teacher is probably the closest thing you're going to come to a true sadist in your lifetime. It's
Yeah, exactly.
I knew that when I said it.
yeah. Okay, so let's go the other way. Pam has saved $250,000 for retirement. Pam hopes, plans, however you want to put it, hopes to live 20 more years after retiring. At 5.2% interest. I'm going to pause here for a second. You notice that interest rate is considerably lower than the other interest rates I've put out there. Typically, when you're drawing money out, this is, you can see we're going to be switching over to the liquidation phase here. When you're drawing money out, you typically put it into safer investments. So the amount that you are going to, your yield, your interest is going to be a lower interest rate. When you're paying in, it's usually a riskier investment, so you get a higher interest rate. Does that make sense? Okay. So at 5.2% interest, how much can Pam draw? Draw just means how much can they withdraw or take out as a payment each month. So as I said, we are now in the liquidation phase. The liquidation phase means we're starting with that lump sum. That is called a present value. And every period, we are taking out a payment. We're still adding in the interest. Until at the end, we get down to a zero balance or close to a zero balance. Now, in the example I have here, we know the present value and we are looking for the amount of that payment. So in the liquidation phase, the amount of the payment can be found by taking the present value. Now the present value is the lump sum. That's the big number. We're trying to find the little number, so that means we're going to divide. Thank you, you had it. It is still 3 open parentheses. The beginning part of this formula will again look very, very familiar. 1 plus R divided by N. Close parentheses. Wow, I'm struggling to write. The power of N times T again, minus 1, close parentheses, divided by still, open parentheses, R divided by N, and here's where it gets different. I'm not going to close the parentheses here. Times, open parentheses, 1 plus R divided by N, close parentheses, to the power of N times T. And I know you're probably at the edge of your paper right now. Close and close. Now, I'm going to write in the numbers that we're going to use for this problem, and I'm going to have each of you enter this. and I want to make sure everybody here that if you have your calculator, please put this in, because some of your calculators have a character limit. What that means is you can only enter so many characters and it goes to an error. Yours does not. Yours is good. So do you. But I want to test and make sure that nobody in the class has one of those calculators with a character limit. Because if you do, I've got to show you a slightly modified version of the formula to use. So we're starting out with the $250,000. Divided by 1, 2, 3, 1 plus 0.052 divided by, is this monthly or annually? Monthly. Draw each month, right? Divided by 12. Close parentheses. Going to draw for 20 years, right? So 240, 20 times 12, or 12 times 20. Minus 1. Close parentheses. Divided by, open parentheses, 0.052 divided by 12 times, open parentheses, 1 plus 0.052 divided by 12, close parentheses, power of 240, close and close. Oops, we divided by, right? 1, 2, 3. $1,677.64.
Yep.
Okay, your calculator should be able to handle it, so let's punch it again. So let's take you through it keystroke by keystroke again here. So it'd be 250000, 250,000 divided by 3 open parentheses, 1 plus 0.052 divided by 12, close parentheses. So the power of 240. Do the right arrow to get out of the power, or do you have to do that in yours? Okay. So minus 1, close parentheses, divided by, open parentheses, 0.052 divided by 12, times, open parentheses, 1 plus 0.052 divided by 12, close parentheses, power of 240, close and close. 1677.64? Perfect. Yeah, and there's a few keystrokes there that might be easy to screw up. Anybody else having problems getting their calculator? Now, I will tell you, many of your cell phone calculators will not do this. You tried it? Yours does? Okay,
No,
cool.
we downloaded one that works.
Good deal. There are a couple out there that you can download. There's like a Math Calc and a couple others that do work pretty well. I think some of them are like 99 cents. They're not horribly expensive. But... Okay, any questions before we move on? let's look at a slightly different example. Peyton wants $2,500 per month to live off during retirement. Peyton wants to retire at 67 and expects. Now, here's the question I always get. How do you know how long they expect to live? It's really a wild guess. But the biggest predictor, the most accurate predictor of life expectancy is the age your parents lived to. So based off family history. You're in trouble? You've already outlived your expectancy, is what you're saying? Uh-oh. That's not good. Well, then there's some paperwork you should maybe get done. Peyton wants to retire at 67 and expects, hopes, whatever, to live, to 85 at 6.9% interest. How much does Peyton need to retire? In other words, what's that lump sum that Peyton needs at age 67 to retire?
Question for you.
Yeah.
On an annuity, it's not really a percent.
It's still a percent.
There's so many different.
There's still a percentage. It's a percentage yield. It's a yield they call it. Yeah. So, this one now, we have that present value, that lump sum. Oops. Try that again. We're going down to 0. We're taking out that payment every month or every period. And of course, we're adding in the interest. This time we know the amount of the payment that is needed, and we're trying to find that present value. So the amount of that present value is the amount of the payment. And yes, you guessed it, the only difference between this formula and the last formula is times. 1, 2, 3. I'm going to fly here for a second, and then I'll pause and let you guys catch up. 1 plus r divided by n, close parentheses, to the power of n times t minus 1, close parentheses, divided by, open parentheses. R divided by n times parentheses 1 plus r divided by n to the power of n times t, close and close. I didn't feel any need to go over that formula in great detail because it's the exact same formula we just did with the exception of times.
Todd, I had a question.
Yeah.
Are we ever gonna do any problems where, oh, sorry. I was just gonna say, are we ever gonna do any problems where the person in the problem depicted actually dies?
No, we're not going to look at what happens if they die early, because there's some legal issues and stuff there that I don't want to get into. That is a good question, but it's not something I'm going to get into. What's the amount left at that age?
We're gonna die in the middle of doing one of these.
Well, then hopefully I'm in your will.
Okay.
So the present value, Peyton's present value. Peyton wants $2,500 a month times. Now this is, remember, the required present value, the present value that would be required to withdraw $2,500 a month. Times the 3 parentheses 1 plus 0.069. This is monthly, so divided by 12. So the power of, what's the power have to be here? Well, it's 12 times a year. What's it?
I was wondering if it was 85 subtract the 67?
You got it. 85 minus 67 is 18 years. So 12 times 18, which is what, 216?
Yep.
So 216 periods, 216 months. Minus 1, close, divided by, open. 0.069 divided by 12 times, parentheses, 1 plus 0.069 divided by 12, close, power of 216, close and close. Let's do this. 2,500. 1, 2, 3. I apologize on the recordings. I've been told that when I'm punching long formulas into the calculator, I sound very angry. The tapping on the screen.
Oh, you do, yeah.
Does it?
Yeah.
So you get 308, 767, 32. Like I said, my screen is sometimes the calculator buttons for some reason are not very sensitive, so I have to really. Did I write it wrong?
308,767, right?
767 at 676. Yeah, thank you.
Don't go on that.
You got it? Not quite yet.
So we can't put in half the equation and get that answer just to make things a little more manageable?
Unfortunately, you have to, if you do that, it might change whether it's a divide or a multiply. So you have to enter the whole thing all at once, or if you need to enter it in half at a time, we've got to modify it in some way.
Okay.
Okay. Still not working out for you?
Yeah, we have this app called Calculator Numbers.
Okay.
Oh, it works, it's just, you have to have the right operator entering the stuff correctly.
It's like you said, there's a lot of keystrokes. There's a lot of chances to make a small mistake there. Every little mistake counts. So let's say that Alex plans to retire at 62 and live to 92 at 8.5% interest. It's something when they do retirement planning, you actually do have to figure out how long you expect to live, life expectancy. Otherwise, you don't want to retire and plan on living till like 85 and then get to 85 and your money runs out and you've got another 5 or 6 years left in you. At that point, you're a little too old to live in a 2-story cardboard box. So at 8.5% interest, how much does Alex need at 62 in order to draw $3,200 per month? I'm going to give you guys about 3 minutes to get that formula written down and plugged into your calculator, and then we'll discuss it. There's a few of you still punching numbers in, but we're running short on time here, so I'm going to go over this one. I've written out the formula here for you. Here we know the monthly payment, the regular payment, and we want to find the present value. So it is 3,200 times 3 parentheses 1 plus the 0.085 divided by 12, because it is per month, so it's monthly, to the power of 360. From 62 to 92 is 30 years. 92 minus 60 is 30. 30 times 12 is 360. Minus 1, close parentheses, divided by, open parentheses, 0.085, divided by 12, times, parentheses, 1 plus 0.085 divided by 12, to the power of 360, and then close it up. Anybody want to share what they got for a number? Go for it. $416, $171, $66. That's what I got. 451. Something went slightly wrong there then. That brings us up to close enough to break time. So let's take our second break. When we come back, there is more fun and amazing stuff that awaits us in the third hour.